Fluorescence quenching is when we add something to the solution that will actually react with the excited state and will prevent it from fluorescing. And so we might have a compound that fluoresces quite well, and the addition of a small amount of something like oxygen might quench that fluorescence, might prevent most of those fluorescence photons from appearing. We're going to go ahead and we're going to use Q as our quenching molecule. And what's going on is our quencher is reacting with that excited state, and it is deactivating it somehow. Later we'll see there's about three mechanisms for deactivation. We won't discuss which one just yet is actually going on, but we can see this is a bimolecular reaction, so the rate is equal to some rate constant. We're going to call it KQ for rate of quenching, times by the concentration of each thing that comes together in our elementary reaction. So we can go ahead and write the mechanism for this process. So we've got excitation of our sample forming that excited state, and it has a rate law. Nu equals the intensity of the absorbed light, I suppose. That's good enough for now. We also have ways for that excited state to decay, so that excited state can turn back into the ground state through internal conversion. So we can go ahead and write rate constant for internal conversion times by S star, so that's a first order reaction here. It's a unimolecular reaction. And remember, internal conversion is where you basically do a conversion into the same spin state, but there's not a radiative transition, so there's no light that comes out. So presumably that excess energy goes to solvent. We also can fluoresce, of course, and so we can go ahead and we can produce a fluorescence photon, and again it's a unimolecular process here, so this is Kf times by S star. And some other possibilities, we can intersystem cross, so we can go from a singlet manifold to a triplet manifold, and we can say that this has a rate equal to the intersystem crossing rate constant times by S star. So you can see these three kind of look exactly the same as each other in terms of their rate form. And there's one more thing here, right? We've got the top mechanism here, so we've got the quenching molecule can react with that excited state and form, maybe we can go ahead and just assume it reforms the ground state again in the quencher molecule, and sometimes that quencher molecule can be energized, so we won't worry about that for now, but we can say that the rate constant here is the second order rate constant KQ. The thing, we're actually going to be quite interested in this quenching rate constant, so we're going to kind of focus our attention on trying to figure this out in the next few slides. So maybe we want to write a rate law for the rate of change of S with time, so we can go ahead and we can calculate the rate of change of that excited state with time. And well, we have only one thing producing it, and that is absorption of photons, and we have a whole bunch of things getting rid of it. So we've got internal conversion, and we have intersystem crossing, we have fluorescence, which is the thing that's easy to measure by the emission of light. And now we've got this quenching possibility. So we've got the quenching rate constant times by the concentration of our quencher times by the concentration of that excited state. We can collect terms here a little bit, and so we can see that we've got a whole bunch of terms here that involve S star, so we can go ahead and we can factor that out. And then we've got internal conversion, intersystem crossing rate constants, our fluorescence rate constant, and then we've got our new rate constant here, our quenching constant times by our concentration of quencher. We can apply the steady state approximation for S star, and the steady state approximation basically assumes that the rate of production and consumption is exactly balanced out. So over time, this concentration is not changing. It doesn't mean the concentration is zero. It just means it isn't changing. And so 0 then is equal to the sum of all this mess here. And so we can rearrange, I suppose, and say that the absorption of photons must exactly be balanced out by essentially these deactivation processes here. And we can go ahead and make use of our last expression when we determine the quantum yield. So the quantum yield, and notice I'm not putting the comma 0 in the subscripts there because that means it's in the presence of a quencher. And remember, that was the rate of fluorescence, so essentially the number of photons that come out thanks to fluorescence divided by the, if you like, the rate of absorbed photons. So that is our I sub ABS in our equation. So we can write this now. So the rate of fluorescence, that's just Kf times by the concentration of that excited state. And the rate of absorption of photons, we said in the last section, right? This is equal to S star times by the collection of all those deactivating rate constants. So Kf and KIC, intersystem crossing, internal conversion, and then that new term here, this quenching rate constant times by the concentration of Quencher. And we can see that these S star concentrations are exactly the same, and so that allows us to write now the expression for the quantum yield in the presence of a Quencher. So again, this comma 0 now has disappeared here, and this is equal to Kf divided by the sum here of Kf and KISC and KIC, and that quenching rate constant times by that Quencher concentration. And you can see this is exactly the same as the expression we derived before. When we had no Quencher, we would write that comma 0 in. If there were no Quencher, then this last term here is basically vanished. And so the expression for the quantum yield in the presence or the absence of a Quencher looks exactly the same at this point. So one of the big things we're interested in is figuring out the rate constant for the quenching reaction. So we need to go ahead and figure this out, and we can take the quantum yield with and without the Quencher, and we can ratio, and we can go ahead and do that on the next slide. So let's see how we can determine the rate constant for quenching from quantum yield ratio. So we've got the quantum yield in the absence of a Quencher, and we saw that this is equal to Kf divided by the sum of all those rate constants for deactivation, Kf, K intersystem, and K internal conversion. And we are going to divide this expression by the quantum yield in the presence of a Quencher, which we saw is equal to Kf divided by Kf plus K intersystem plus K internal conversion plus that rate constant we're interested in, Kq times by Q. Gosh, those are kind of some big expressions there. So we can go ahead and we can notice a couple of things here, actually, and this will be important later. So we'll go ahead and we'll come back to this. So make sure you write these in your notes. So this top expression here, Kf over the sum of those rate constants, that is Kf. And if you remember, the sum of all those rate constants inverted is tau. And remember, we put a subscript 0 down there to let us know that this is the lifetime of the excited state. This is the lifetime of that fluorescence decay in the absence of a Quencher. And on the bottom, we can see that essentially we've got exactly the same expression. It is Kf over the sum of all those deactivating terms. And so this is going to be the lifetime in the presence of a Quencher. So notice we leave off the 0 there. The 0 is telling us there's no Quencher, and when we leave it off, it's telling us there probably is a Quencher. So we'll come back to that for now. So I've put those in green, so we're not going to use them for a slide or two, but pay attention. You can see that some of the terms are exactly the same on the top and the bottom, and so we can do some cancellation. We can see the Kf cancel out on top and bottom, and we are now left with sort of reciprocals of reciprocals. So this is kind of a pain, but we can go ahead and write that ratio of quantum yield on the left, and it is equal to, so we're kind of flipping the double denominator there on the bottom here, so that's Kf plus KISC plus KIC plus KQ, the thing we care about, times by Q. And now this is going on the bottom, right? This stuff here is going on the bottom. So this is Kf plus K intersystem plus K internal conversion. And you can see, right, that the first three terms here are exactly the same in the numerator as the denominator. So that is 1 plus KQ divided by Kf, KISC, and K internal conversion. I think I left off an I there before. And this is the same as 1 plus KQ times by Q, and then the reciprocal of those three deactivating rate constants, we call that the time constant, and that's the time constant in the absence of a Quencher we saw before, so that's tau 0. So let's go ahead and just kind of rewrite that on the next slide. So we're about at the point where we've got the Stern-Volmer equation, and we've got the ratio of the fluorescence yield in the absence of a Quencher with the absence. And these are all pretty easy measurements to make, to be honest. And so you basically just put your sample in a big box and shine photons in, and you count fluorescence photons out. And normally you shine the photons in at 1, angle and you measure the fluorescence photons at 90 degrees. And so you're just counting what goes in versus what goes out. And you do the same thing in the presence of a quencher, and you do that. So those are steady state. Those are pretty simple things to do. You can buy these setups for a few $1,000s to $20,000 for something that's publishable. And when you ratio these, this is giving you some information about this rate constant here. And we can see lovingly enough, right, this has the form of a y equals mx plus b equation. So if we plot the ratio of quantum yields on the y-axis and we plot the concentration of the quencher on the x-axis, then we can see that this would be a y equals mx plus b. So tau 0 times by that quenching rate constant would be the slope, and our intercept would be exactly 1. So we can make these Stern-Volmer plots here. So let's go ahead and sketch out what one of these would look like. So we're going to plot the ratio of the quantum yields, and we're going to plot versus the concentration of our quencher, and we're going to get a straight line. Presumably both tau and k are positive quantities, so the straight line will slope in an upwards direction, and this is what this kind of plot should look like. The slope of this plot is equal to the things we're interested in, so the quenching rate constant times by tau 0. And actually one real problem with this technique is we need to know tau 0, so we need to have an idea what the lifetime in the absence of a quencher is. So unfortunately that does mean we have to do, probably a fairly expensive experiment. So we need to come in with a pulse of light, right? So this light's going to be absorbed by the sample, and then we're going to watch the fluorescence decay. So that pulse of light causes the molecules to absorb and form excited states, and then those excited states, right, are going to decay away with that exponential kind of function. So e to the minus t over tau, and in the absence of a quencher, right, this is tau 0. So we can fit this data, right? So I used to do this in graduate school, right? So you'd collect thousands and thousands of data points here, and you'd basically minimize the sums of squares times by some weighting function, and eventually you'd find the lifetime that best fit this decay. So it's kind of a bummer. So you need to be able to measure the lifetime. These kind of setups cost about 100 thou, whereas measurement of these cost, maybe a couple of thousand if you're looking for something quick and dirty.